Okay, let's start. Towards the end of last class, we started to look at the modeling of noise in a resistor. So, we saw that resistor with a value R will generate some noise, and the way we can model it is as follows. We can assume that the resistor is noiseless, but the noise is generated by some series voltage source Vn. So, this is a noiseless resistor. So this is my noisy resistor, and this entire block is my noisy resistor. And the power spectral density of this voltage source was 4 kTr volt square per hertz. Now the alternative way to model this is to take this resistor and have a parallel current source, just a source transformation. So what will be the value of this current In terms of the voltage Vn? Vn by R. So the current will have a power spectral density which is 4 kT by R. Okay, fine. So just like a resistor, even a MOSFET will generate noise, and it turns out any element that dissipates energy in general will generate some thermal noise. So of course in a MOSFET, when we apply some gate to source voltage and drain to source voltage, we expect a constant current, but again due to this random noise, we'll have random fluctuations over this expected drain current. And of course only it will generate noise only if the transistor is on, and when it is on, it can either be in strong inversion or saturation, as we know it. And when it is in saturation, the noise in this drain current can again be modeled as a current source in parallel to this noiseless MOSFET, and the power spectral density of this current is given by 4 kT gamma times Gm, where K is Boltzmann constant, T is temperature in Kelvin, Gm is the transconductance at the operating point, and this gamma is an empirical constant. It's not related to the body effect coefficient, it's an empirical constant. It's usually 2/3 for within quotes long channels, but of course for modern transistors this could be close to 1 also. It's a constant. So now when the transistor is in linear region, we'll again have this thermal noise, and in linear region you know that MOSFET behaves like a resistor, right? And what will be the value of this resistance? Huh? Yeah, I mean, okay. What is the current in linear region? Yeah, okay. Let's say mu Cox W by L times. Okay, I'll write it like this into VDS, right? And the resistance is basically derivative of conductance is derivative of current with respect to VDS. So we'll have some on conductance G on, and of course since it behaves like a resistor in linear region, even the current can be modeled as 4 kT times G on. So okay, cool. So this is thermal noise.
Derivative with respect to
VDS. I mean it acts like a. So you can see here, if I neglect this VDS by 2, which will be very small, it is linearly related to VDS. So this portion is my conductance, right? This is thermal noise, but in MOSFET we also have another source of noise, which is called the flicker noise, or also called 1/f noise. And I will not explain the mechanism in detail. It is essentially due to some impurities in the fabrication process. We can have some random traps trapping the charges and releasing. So even the noise due to this flicker noise, we can model it as a parallel current source. The power spectral density of this flicker noise is some constant K. It's not the Boltzmann constant. I will use a capital K. K into Cox by WL square to 1/f. I mean, point to notice, unlike the thermal noise, which was flat, which had a flat pass spectral density, the pass spectral density of flicker noise is inversely proportional to the frequency. Okay, and thermal noise is a fundamental phenomenon. It's basically from thermodynamics. We can show that we'll have this kind of noise. But flicker noise is not a fundamental phenomenon. It is arising due to some impurities or imperfections in the fabrication process. Okay. So what that means is, let's say you take two transistors from two different processes. If both transistors have the same transconductance, the thermal noise pass spectral density will be 4 kT gamma gm in both. But the flicker noise pass spectral density can be extremely different in the two cases, because this constant case depending on the process. So flicker noise is kind of process dependent, whereas thermal noise is more fundamental. So let me just close this. So if I sketch the pass spectral density of flicker noise, let's say sketch it in a log scale. This is log frequency, this is again the pass spectral density in log. How will it look like? It will have minus 20 dB per decade slope, so it will do this. Okay. Now, along with the flicker noise, we also have the thermal noise. So if I plot thermal noise also, we will have something like this. This is thermal noise. Now the total noise will be sum of these two, and so it will probably look something like this. Okay. And some jargon. So this point where the flicker noise becomes equal to the thermal noise pass spectral density, it is called the 1/f corner frequency. It simply says what is the frequency till which my flicker noise is dominating. Okay. And again, this is again variable with process. It can be hundreds of kilohertz or even few megahertz. Okay, great. So in short, the total noise in the MOSFET, we have both thermal noise and flicker noise. So we can model this noise using two current sources like this, one for thermal noise, one for flicker noise. Okay. And I mean, in our calculations, we'll most of the times we'll ignore flicker noise. We'll consider only thermal noise. Of course, the same calculation works good for flicker noise also, but for ease of analysis, we'll not consider flicker. Okay, so let me write it once again. So for MOSFET, the thermal noise, pass spectral density is 4 kT gamma gm. This is the current. Okay. Similarly, for a resistor, it is 4 kT by R. This is the current pass spectral density. Okay. So these two, please remember. Cool. So now let us say I have a big circuit. So we'll model it like a network like this. Okay. So this has, let's say, multiple noise sources. And for example, I'll consider two resistors like this and a MOSFET. I've just taken it out separately, and this is my output. Now each of these is going to generate some noise, so I can model it as a series voltage source for the resistors, or I can do also parallel current source. I'll do that maybe. So we can model it using parallel current sources. Again, notice that the polarity of these current sources do not matter. It's a random signal. I am only interested in the mean squared value pass spectral density, so the absolute polarity doesn't matter. I can choose anything. Okay. So let's say this is IN1, IN2, IN3. How will I find the total pass spectral density at the output? Summation of? Yeah, I mean, note that all these noise sources are uncorrelated first of all. Okay, so let me start from here. And this network itself could be nonlinear because you have lots of MOSFETs. but we are dealing with noise. Noise will be, I mean, you can say that noise has extremely small amplitude. So even if the network is terribly nonlinear, our small signal linear approximation holds quite good. Okay. Holds very good for noise because noise amplitudes are going to be really small. So you can think of this as a linear network. So you have multiple input sources. To find the total output, let's say I find V out of f. I can find it using superposition, considering only one source at a time. So this, let us say it is some in1 of f times say some z1 of f plus in2 times some z2 of f. The transfer function I am saying is z3, right? Some impedance. So this is my spectrum or the Fourier transform. If I want to find the path spectral density, this comes basically due to linearity. Okay, let me write that also. I am able to write this because the circuit is linear, at least for noise. Now, if I were to write the path spectral density, how will it look like?
Each function multiplied in gains for each.
Yeah, this in1 of f times mod z1 of f square, plus I will do the same thing for others also. Okay, and I am able to do this because all these noise sources are uncorrelated. Okay, again you do the same things, you will find that all the cross terms will arise. Uncorrelated noise source 0 mean, so cross terms go to 0. And in general, if you have n noise sources, you can do it. You take the kth noise source, find its path spectral density, find what is the transfer function from that noise source to the output, say that is some hk of f, and then you do it for all the noise sources starting from 1 to how many noise sources you have. So cool. So now we know how to find the total path spectral density at the output. Now, although this is nice,
So you almost like series sources, right? It's a current source. So it doesn't matter if you choose
right.
current sources or some.
Correct.
Would that make a difference if you choose some of them as current sources?
Nothing will change. I mean, it's if you have a circuit here, this branch I can always replace it as like this, right? As long as this is Vn and this is Vn by R, both are identical, so nothing will change. Okay. So like you mentioned, I don't have to have parallel current sources for everything. For some of them, I can model the noise using series voltage source. Depends on the circuit. For sometimes you'll find modeling with parallel noise current source will be easier. For some things, voltage noise source might be easier to calculate. Okay, so now we can find the total path spectral density at the output, but this is not a great measure to compare different circuits, simply because the total path spectral density at the output could be really large if my circuit has a large gain. Okay, so it doesn't make sense to compare two different circuits by looking at the total noise spectral density at the output, because it depends on the gains of the individual circuits, right? So what we do is this is my noisy network. I have found what is the path spectral density at the output, but this is not a good measure. So what we do is the following: we assume that this network is noiseless and the entire noise is arising due to some voltage source that I am adding at the input. Okay, I'll call it Vn in, and this is my, so whatever is within the dotted box is the overall noisy network. Okay, and if let's say the transfer function from the input to the output is some h of f, what can you say about the path spectral density of this voltage source? at the input.
Being as of
In terms of the output path spectral density. What I'm saying is, see, at the output I have some path spectral density. I'm modeling it as though the entire noise is coming from this guy.
as out of f upon h of s.
Yeah, is that okay? So the only thing is now I can find that this path spectral density times the transfer function from here to here, which is h of f. So mod of that square is the output path spectral density. Okay. So this basically, is V out of f. So what we are basically doing is, whatever noise we have at the input, we are referring to at the output whatever noise we had, we are referring it back to the input by dividing it by the appropriate gain. That's all. So this is this Vn in is called the input referred noise. Now to find this input referred noise, we don't have to look at the output voltage. We can also look at the output current. Okay, so let me show that once. So instead of looking at the output voltage like this, I can go and short circuit the output and find what is the short circuit current. So here also I'll do the same thing. I'll short circuit this guy. Okay, and then I'll have S I out of f, and I'll find what is the transfer function from this source to this current. So voltage to current, so it will have some admittance. Okay. So this by mod y of f square. Right, because I am basically trying to model all the noise into a single voltage source. For that I can either look at the output voltage or the output current. Okay. And in many times with respect to MOSFETs, since we'll be modeling the noise as a parallel current source, finding the short circuit current is relatively easier. Okay. So you can do either of them. You can find the open circuit voltage here or the short circuit current. Find the transfer function from this noise source to the output here, divide it by the transfer function square, and you get the input referred noise. Okay, great. Now this notion of modeling this noise using a single voltage source at the input, so it works quite good, but there are some limitations. Let me mention that. So this is my overall network. Okay. So let us say here I apply some input voltage. Now it's clear that the total input that goes into the network is the input plus noise, and we'll have contribution due to the signal and the noise. It's done. And if you were to find the contribution only due to the noise, again we'll use superposition. Assume that the input is not there, so we'll short this. And you see the same thing, this noise is appearing across this network, it sees some transfer function and it comes at the output, it's all fine. Okay, but the actual problem here comes. So the actual problem comes if this input voltage that we are adding has some series resistance. Okay. Now remember that this series resistance is not under your control. This is a part of the source or the previous network that is driving our network. And when you are modeling your network for noise, you can't include RS, right? Because RS is not it can be anything. Okay. So now in this case, let us try to find out what will be the noise at the output. So for that, I'll assume that the input is not there. So maybe I'll paste it here. So the input is 0, so I'll only have the resistance Rs. Okay. So in the earlier case, maybe I should go there. In the earlier case, when I didn't have RS, and when I tried to find the noise at the output, I had this. So whatever input referred noise we had, that was directly appearing across the network, and we got the noise. But now you see that this guy is now getting divided between RS and whatever input resistance I have for the network. Okay, so not everything is now appearing across the network, right? And in fact, if the input impedance Zn, if Zn is very small, right? I'll say small compared to RS, then it will appear as though only a very small fraction of the noise appears at the input, and it will appear as though I have very small noise at the output. Isn't it? But that's not the case, because the network is generating the same amount of noise. The issue is because the way we have modeled it, it is not capturing the effect of RS. And this is not a problem if my input impedance is infinity, right? If my input impedance is infinity, irrespective of RS, whatever noise is here, that will appear across the input, and we are okay. The issue comes when we have some large enough small input impedance or a large source resistance RS. Is that point clear? So the problem is because the way we have modeled it is not capturing the effect, and it's creating issues if we have a large source resistance or a small input impedance. So if that is the case, let me copy this. So modeling this noise using this voltage source alone is not enough. So we need to add something here. So what do you think we can do so that even if there is a very small input impedance, see now we can't just have this voltage source modeling the noise. We need to have something else to model the noise along with the voltage source, and that something else should be such that if I have a very small input impedance, that some second source that I am adding, that should pump in the entire energy into the low impedance. Should some current source, right? So what we should do is, along with this voltage source, we also add a current source. I'll call it IN in. So now you see, if the input impedance is really small, the voltage source is not pumping in any energy into the network, but the current source will pump in all the noise current into the network, and that will generate the noise. Is that okay? So this is what we'll have to do. So this is the complete model. And again, I've qualitatively explained, but you can rigorously prove that we can model it like this. So we need both input referred noise voltage and a noise current. Okay, we need both of them to capture to model the noise of the network, so that it doesn't depend on the source resistance we might have here. Okay, so we can have any source resistance here and it will work. And let's take some extreme cases. Oops, what happened? This is RS. So let's take some extreme cases. So let us say my RS is 0. So RS is 0, this is basically short. So now I have both voltage and the current noise. So which of them do you think will be dominant? Voltage noise, because this voltage is going to fix the voltage across the network to its value, and in fact this current will not provide anything, because this current source will, the entire current will flow into the voltage source, right? Again, can you superposition to find the contribution from both? To find the contribution from the voltage source, you will open the current, so the entire noise voltage appears across the network. To find the contribution from the current source, we will short the voltage source. If we short it, the entire current is flowing here, nothing goes into the network. Okay. So in this case, all noise is due to my voltage Vn in. So similarly, let's take another extreme. What is other extreme?
RS is greater than Z.
Yeah, I mean infinity, right? So infinity means it's open, right? Now if it's open, which of the sources do you think is current source? Because voltage source is simply floating. So in this case, all noise is due to my current. Okay. And if we have any other resistance, I mean any other RS value between 0 and infinity, both of them will be there. So what this means is, if I have RS to be 0, I don't need Vn in, so Vn in is essentially 0, right? Because entire noise is coming from the current. Oh sorry, it's not right, sorry, I made a mistake, yeah, sorry. Okay. Is that point clear? So we need both of them to model it, and if RS is 0, the entire noise comes from Vn in, and if RS is infinity, entire noise comes from the current. Okay. And another point, if my input impedance is infinity, I actually don't need the current at all, right? Okay, so in that case, you can find the current will be 0 actually, if my input impedance is infinity. Cool. So let's now quickly see how we can find this input referred noise voltage and current. So now we'll have to find these two, and to find, so let's say first we want to find this voltage Vn. Okay. So we need to we need to contrive something so that the entire noise comes due to only the voltage. And you see that if I choose RS to be 0, entire noise is arising only due to Vn. So what we can do is the following. I'll choose RS to be 0. Okay, and this will be by noisy network. So here again RS is 0, I'll short it like this. So I can find the total SV out of f. This I know, I can find from each noise source to the output what the transfer function is, blah blah blah. I'll find the output voltage part spectral density, and then from Vn to output, let's say the transfer function is some h of f here. Okay, so this by mod h of f square. This is very similar to what we saw before also. Okay, and I mean, as I mentioned again, you don't need to look at the output voltage. You can also look at the output current to find the input referred noise. So instead of looking at the voltage here, I can also short the output and find the current.
No contribution due to current source from here in this.
Sorry?
No contribution of current source.
Yeah. No contribution of current source here because I have shorting the input, right? Yeah. So now I will find the transfer function from the input source to the output current. So that will be some y of f. So this will be the SI out by mod y of f square. Okay. So this way we can find the voltage Vn in. Now we'll also have to find the current. So for finding the current, I'll again try to form a case where the entire noise comes only due to the current, and you already know that will happen if my RS is infinity. Okay. So what I'll do a very similar experiment. I'll just copy paste it. Paste it, is it okay? So I'll now open this guy. If I open it, the voltage source is not playing any role, it's gone. So the entire noise is coming only due to the current. So I'll find some transfer function from the input current to the output voltage, some impedance. So my current power spectral density, I will find it like this. Okay. I mean, same thing you can do with the current also. So this is now will not be dominant. So this will be some h of f. Okay. So it will all be clear if you look at couple of examples. So we'll just write it for completeness. Okay. So let's look at few examples so that you will understand. And again, I want to highlight once again, if my input impedance is infinity, my INN is 0. Okay. Cool. So let's start with some simple case. So I'll start with a common source amplifier. Okay, RD. This is the input, drain is the output. And for all our noise calculations, for most of the time we'll ignore R0 to simplify our analysis. Okay. So here I'm interested to find both the input referred noise voltage and the noise current. So what is the input impedance here? Infinite. If I ignore the gate capacitance, which I'll do for now, the impedance is infinity. So what can I say about the noise current? 0. So I just need to find only the voltage. Okay. And for finding, so basically we'll be modeling the network like this. So we'll assume that the MOSFET and the resistor are all noiseless. So the noise is all coming only due to these two guys. And I know for a fact this is not playing any role, and only V and in is there. So from here, what should I do to the input side so that the noise is coming due to V and in? I should short it, right? So same thing, I will short the input here, maybe show it this color. Okay. So I'll do the same thing in the network here. I'll short the input. Done. So now I have two noise sources. One is resistor, one is MOSFET. So now I can find the either the output voltage or the output current. I choose to find the short circuit output current. Okay. And the network is non-linear, but noise is really small. So I can do my small signal approximations everywhere. So VDD is incrementally short. Okay. So I have two noise sources. Let's find the noise from each of them separately. So let us say I model the noise due to the MOSFET as a current source like this. Say it is some IN1. What will be I out? I out will completely flow into the short circuit. Nothing will flow into the resistance RD. So I out is simply IN1. Done. So the next noise source is due to the resistor. Again, the direction of this current doesn't matter. I can choose any random direction. Okay. So I out. So if this is IN2, what is I out now? Again, same thing. The entire current flows through the short circuit. It's IN2. That's why it's easy to model it using easy to find the short circuit currents. Okay. So my total I out is going to be sum of the two. So my total power spectral density for the output current will be the sum of the individual power spectral densities. For the MOSFET, it's 4 kT gamma times GM. For the resistor, it is 4 kT by RB. Let's say it's RB. Okay. So now the only thing pending is to find the transfer function from this guy Vn in to the output current. Once I know that, I can divide this guy by the transfer function and get the input referred noise, right? Is that logic okay? So please tell me if it's not clear. Okay, fine, cool. So let's quickly find the transfer function. So I am applying a small signal Vn in at the gate, right? Oops. So here I am applying a small signal Vn in at the gate. I am interested in finding the current. What will be the current in terms of
minus
yeah? Let's say let's not worry about sign here. It's m times Vn. Okay. So the transfer function is simply gm. So if I were to find Svn in of f, I will take this entire guy divided by gm square. That's all. So if I do that, I'll have 4 kt. I'll just write the expression and finish. This 4 kt by gm square rd. So I can write it like this: 4 kt by gm. I'll take out. I'll have something like this. That's all. Okay. So next, let's look at a case where we have both the. Here we didn't have to calculate the noise current because the input impedance was infinity. I mean, again, if you try to calculate, what will happen is this: you will find that if you check here, you calculate everything finally, and then you will try to find the transfer function from this guy to the output. Since it is an infinite input impedance, the transfer function will blow up. So when you divide the transfer function here finally, you will get something. See, what I am saying is, even if you try to find the noise current for this case, you will find some output noise path spectral density. You will divide it by some transfer function, and that transfer function will blow to infinity because this is an infinite input impedance, right? Because if I try to find the transfer function from let's say this current source to the output, what do you think that will be? No, let's say I have some current here and I'm trying to find what is the output current. This is what we'll have, isn't it?
We cannot compute current.
Yeah, it's basically it's an open circuit, it's infinity, right? This voltage will become infinity, isn't it? So the transfer function itself will become infinity. So the path spectral density of the current will become 0. So that's why you don't have to calculate the things for noise current. So in simple, if the input impedance is infinity, the current is 0. So next, let's look at a common gate. So here is where I apply the in. So here, what is the input impedance? I'll assume again R0 is infinity. It's 1 by gm. So I'll have both voltage and current. Okay. So let's try to find. So let me draw the model I'll have. So this is the noiseless network. So here I'll have both the voltage and the current. So first I want to find the voltage. So what should I do to the input here? I have to short it. If I short it, this current is not playing any role. So now I'll do the same thing here also. I'll take this guy, short the input. Okay, and I'll try to find the short circuit current like this. So again, I have two noise sources, one due to the resistor, one due to the MOSFET. So I'll write it directly now. So I'll have two current sources like this. So what do you think the output current will be? Sum of the two. It's similar to what we saw before. So my S I out of F will be same as before. It's 4 kt gamma gm plus 4 kt by RT. Now the last step is to find the transfer function from my input referred noise voltage to the output short circuit current. And what do you think the transfer function is? Oops. I mean, this current source is not there, you can ignore it. I am applying some Vn in at the source. what will be the incremental current? Yeah, you take care of polarity, but I mean in this case it doesn't matter. So the transfer function is 1 by gm, I out by Vn in, right? Sorry, gm, you're right, sorry. So I'll basically, to find the input referred voltage, I'll take this guy again divided by gm square. This will give the noise, input referred noise. Now let's find the input referred noise current. So I'll do the same thing, I'll draw the circuit once. Sorry, this is the input. So let me draw the model so it becomes clear to you. So what should I do to the input to find the noise current contribution? I'll open it, so I'll leave it as such. So this guy is not contributing. So I'm going to open the input now. This is Vn. This is incrementally short. That's it, open. I'll find the short circuit current. So first, due to the resistor, I call it IN2, so I out is IN2. Straightforward. Then let's look at the contribution due to the MOSFET. So for the MOSFET, I'll have something like this. So what do you think I out is? 0, IN1? 0? Is it okay? So this current has to, I mean, this is a open here, right? So whatever current comes has to go here. So nothing will go into I out. Okay. I mean, you can write KCL and find out, but yeah, I out will be 0. Okay. So in this case, the only noise current is due to the resistor. So my S I out of F is 4 kT by R. The last step is to find the transfer function from my input current to the output current. So what is the transfer function? This is I out. 1, it's basically current buffer. I assumed infinite R0, so no need to worry. This entire current will flow. So my IN is same as I out here. So my input referred noise current pass spectral density is same. Is that okay? So we have some time, so please try to work out this one. I'll stop recording also, you can work out here.